Energy. Energy. Yes, we love to have energy. It's good to do that. We're going to talk a little bit, a very, very small introduction to energy, and then we'll do what's called some specific heat calculations. That's actually what our lab is going to be over the next time we meet. But let's talk about energy first before we get into the specific heat stuff. Energy, again, physical and chemical changes are always accompanied by a change in energy. Now remember, energy is not created or destroyed. And it's not something you can hold in your hand, which is kind of crazy. But it's around us everywhere. Since energy is not created or destroyed, it just simply changes places. It moves around, okay, which is kind of neat. The energy changes occur between a system and its surrounding. So like if I were doing an experiment in this beaker that had some water, and that's pretty much what our setup will be for the lab the next time we meet. We'll have actually boiling water, so it will be boiling. It won't be just hot, it'll actually be boiling. And so we're going to take the Bunsen burner and actually incorporate heat into the water. The water will absorb that energy from the Bunsen burner, and then we're going to do something with that hot water. Okay? So essentially what we're doing is we're transferring the energy from the methane gas through the flame into the water and then into something else. So we're moving this energy around. The system is the portion of the energy in the universe under consideration. The surroundings is everything else. So this is the system right here, and then the surroundings is everything else. So if I lose heat from this, say I boil this and it gets warm, is it possible for this energy to go somewhere on Mercury? Yes. Yeah, it's going to be kind of far-fetched, but yeah, it's possible that that could take place. So energy is just moving around, and I'm glad that it is. Energy transfer, the term energy is the capacity to do work or produce heat. In other words, whenever we exercise, we're actually using energy to do the exercise, to run fast, to lift weights, or do it, whatever it is that you do, to walk, to breathe. So energy is the capacity to do work. When you no longer have any energy, you're done. Okay, so we like that idea. The total energy in the system is the sum of the potential energies and the kinetic energy. Now, we're not going to do any of those type of calculations in this class. In AP, we will. That's called thermodynamics. We don't get into thermodynamics here. We just get you to the basic stuff. Heat is energy that's transferred from one object to another. Now, I want you guys to do an experiment. It'll work out well here. I want you to take your hand and somewhere on the desk, okay, somewhere on the desk where you haven't been touching or somebody else hasn't been touching, I want you to feel it. Okay. Initially, how does that feel?
Cold.
Cold. Okay. Okay. Now, take your other hand, leave your hand there, take your other hand and feel the air. How does that feel?
Warm.
It's like you can't feel anything. It's kind of like.
What do you mean you can't feel anything? It's the same temperature.
Yeah.
It feels warm.
Answer me this. Does it feel the same? No. And you want to know why? Because when we're feeling the air, we're not losing as much energy to the surroundings. And I would dare say, the majority of you, your hand is warmer than the air. Your hand is losing energy to the surroundings. When you put your hand on the desk, why did it feel cold? Oh, I heard something about it. It's sucking energy out of you. Actually, what's happening is you are trying. Whenever you touch something, the energy, whichever is warmer, the energy goes from the area of higher concentration to lower. So in that case, the desk, around 72 degrees Fahrenheit, okay, or 22, 23 degrees Celsius, isn't as warm as your hand, so the heat leaves your hand to help warm up that desk. So when things feel cold, when you touch something or someone that feels cold, that thing isn't as warm as you. So you're losing energy. So whenever you touch somebody, in other words, the church that I used to go to, at some point they'd always go around and shake hands. It would always be this, inevitably, there would be this old woman just walking around looking for the young people. Because, I mean, I swear, when you touched her hand, it felt like an ice cube. But what is she feeling?
Warm.
Oh, these kids are so warm. Okay? What they're doing is they're sucking the energy out of you. They're stealing your youth from you. Don't shake hands with old people, in other words. Okay? But the reality is, when you touch something that's not as warm as you, okay, you're losing energy to that, or heat. Now, when you touch something that's really warm, what does that do? Now you feel the heat, or it feels hot, like babies. When I had Sam, and he was 1 year old, or younger than one, as a newborn, those things are like little hot pockets type things. They are warm. Yeah, they can't think, they can't talk, they're just blobs of baby. I mean, come on. However, you're holding that baby and it's like, man, that thing is so warm. If that kid could talk, you'd be like, get your hands off of me. Trust me, anytime you feel something that feels warm, it feels cold. And again, heat is never created or destroyed. It's just, it's out there. It's, so, all right. It's out there. I can't remember. We talked about a joule earlier on.
Yeah.
Okay. So we're still using joules here. And again, it's a joule that's a Joule. Endothermic, exothermic. Two terms. Okay. If heat is leaving, exo. If heat is being absorbed, endo. Pretty easy to remember. And I have kind of a simplistic diagram here, that if we start off with reactants that don't have very much product or very much energy, but the products do, that absorbed energy. So if you want to draw a little line where energy's coming into the system, that's fine. And then if we start off with a lot of energy for the reactants and something explodes, it doesn't have as much energy anymore or burns off. So endothermic, exothermic, and again, if it absorbs energy, that's endo. If it leaves, it's exo. And again, activation energy we'll talk about when we do chemical reactions. We're not going to talk about activation energy yet. Factors that determine heat transfer. The amount of heat transferred depends on three factors. The capacity for the substance to absorb the heat. Okay. In other words, trust me, I can absorb more heat than this bottle of water can because I'm bigger for the most part. The mass and the actual change in temperature. Okay. Specific heat. Specific heat deals with the ability for something to absorb energy and hang on to that energy. Okay. There are some things that absorb energy rather quickly and then lose it just as quick. Like skillets, frying pans, whatever. Did I say that right? Is a skillet a frying pan?
Yeah.
Okay, I don't know my cooking terminology.
No, it's a pan.
It's a pan? Whatever it is. Something metallic. Metals are notorious for having low specific heats, and we like that because we don't want to have something that takes a long time to heat up and then a long time to cool down. So, like our cookie sheets that I make pizzas for Sam on, that thing gets really hot really fast, but if you want to cool it down, what do? Run water under it.
No, that warps it.
I don't care, it's not mine. It's my wife's. She goes and buys more. Okay, so if you really want to cool it down, just run water over it. That water absorbs that energy really quickly, and it loses the heat from the metal. That's okay. However, be very thankful that water has a very high specific heat. In other words, when we heat this up, does it heat up like that? No, it takes a while. And it's a good thing that it takes a while to heat up because what that means is it takes a while for it to cool down. So when I go to Florida for Christmas, I'll be able to go swimming in the ocean even though the air temperature might be only in the 70s because the ocean hasn't lost that energy yet, which is nice. The law of conservation of energy means that in an insulated system, the heat lost by one quantity of matter must be gained by another. In other words, I can't heat this up and then it'll stay in there without something happening. In other words, if I heat this up and let it set on the table, if I come back, say half a day later, will it be the same temperature? No. It actually starts losing heat to its surroundings. And what that is it's trying to heat up the surroundings to the same temperature that is. Especially in January where the fire alarm's gone off and it was close to like 10 degrees Celsius out, way below the freezing point for water. And I know that kids were in the swimming pool. If you were in the swimming pool and you went outside when it was well below freezing, what are you going to notice?
It's cold.
That it's really cold. All right? The reason why it's really cold or it feels really cold is because immediately your heat is trying to heat up the surroundings, which is the atmosphere. So it's a losing effort. You're losing that heat quickly. So when you wear a winter coat in the winter, does it make you warm?
Yeah.
No, it does not. What does a winter coat help to do? It insulates you. It slows that rate in which the heat's trying to heat up the surroundings. So winter coats don't keep you warm. I mean, they don't warm you up. They keep you with the heat that you have. So like if you keep a coat in your car and you park your car outside, then you jump into the car and go, "Whoo, it's cold," and you put that cold coat on, whoo, you're not going to get cold. You're not going to get warm. All right. So that's why you keep your coats in the house where it's quote unquote warm. Okay, so it'll be the same temperature as the house, and then when you walk out, it's already warmed up for you. Just some advice. I know you like the thing. The transfer of heat takes place between two quantities at different temperatures unless it generates its own energy, until the two are the same temperature. So all the inanimate objects on my desk that I haven't touched or done anything with are the same temperature as the room. Okay. So these things fluctuate in temperature, so when they turn the heat off in the weekend and it gets down to 60-some degrees in here, everything gets down to 60-some degrees. Also, we feel cold at night when we're not really active because we're not generating that much heat. That's why we want to put covers on to help slow that process down. I like it when it's cold, yeah. All right, here's the equation that we're going to use. This is for specific heat. And I want you to write some things on here. The Q actually is your heat, or energy. And the unit for that is joules. Okay, so we'll be doing some calculations with this here in a minute. The M represents your mass, and that'll be in grams. Let's skip the C for a second. Delta T is your temperature. Actually, what does the delta mean, or the triangle? Does anybody remember what delta?
I forgot.
Change in temperature.
Change in temperature, very good. Okay, so we start off at one temperature and we finish at another temperature, so that's your change. And then the C is our specific heat, okay? And we'll do some calculations with that. Now, technically speaking, the delta T is your final minus your initial. However, for what we're doing, it's just a change. Give me an absolute value for that, okay? All right. And let's not do that. Let's pass this out. Take a look at the sheet I just passed out. And again, what we're going to be doing, this is actually question 2 is like what we're going to do on the lab the next time we meet. But this is the equation that we're using. And yes, you'll be provided with this equation. You just have to know how to use it. And what's even better is you'll always have 3 of the 4 variables. So whenever we're working this out, you're just solving for the unknown. However, you have to know what is what. So like again, the Q represents your heat or energy, and again, that's in joules. The mass is in grams, the delta T is in degrees Celsius, and the specific heat, the C, is our unit where we have, it's a really crazy unit, and it looks like that, where it's joules over gram degrees Celsius. So it's a really nutty looking derived unit, okay? But again, sometimes I'll give you the specific heat, other times you'll calculate it. Or I might ask you for something else. So let's look at question number 1. It says a certain metal, practice problem number 1. A certain metal has a specific heat value, 0.622 joules per gram degree Celsius. The question is, what is the mass of this metal if 7,422 joules of energy was used to warm the metal from 25 degrees to 422 degrees? So what we know is, we know C, we know the Q, we know the change in temperature. So which variable are we looking for?
Delta T.
Mass, M, mass. So what we want to do, and again, we have that equation, and what I want you to do is I want you to put all the known variables on one side of the equation. I don't care which side you put it on, but there's probably a logical side than others. Since we're looking for the mass, we want to make sure the mass stays in the numerator. So we're going to divide the specific heat and change in temperature on both sides. Remember how we worked those out before? So our equation looks like this, where it's C over delta T, which is equal to our mass. Okay? So I want you to show that first. Now that doesn't say cat, that's actually specific heat times change in temperature. So we have our variables rearranged. Once you have the variables rearranged, now we plug in the values with the units and keep the units in there. So our heat that's given is 7,422 joules. And the specific heat value is 0.622. And that's joule. And again, I'm going to write this initially. However, I'm not a big fan of two divisors. So where is the grams and joules degrees Celsius in relation to this joule here? Up top. So I'm just going to go ahead and put it up there. Okay, just to clean things up. Now, how you do your units is fine. Just make sure you're showing them. So that's saying that this is on the opposite side of that because, again, it's a specific heat value. And then the change in temperature, let's just get an absolute value. I know that technically speaking, delta T is the final minus the initial, but I don't want any negative values here. So the difference between 422 and 225 is what? 97. And that is degrees Celsius. Okay, so before we do the calculation, what units can cancel out? Joules can go away. And degrees Celsius. Good. And by doing that, that might make it a little easier for you to see, okay, what's left? Grams, which is mass. Okay, so that really works out well. Let me use the fancy calculator.
What about T?
What is T? Delta T?
Oh.
Yeah, that's what we took the difference of.
I thought delta and Q were separate.
So it's the combination of those two temperatures.
Whoa. This number's supposed to be really large.
Well, we'll see here.
Like, really large.
So 397. So like 3.01 time. Oh, I'm sorry, 30.
That's what I got.
Anybody else get a number?
How'd you get 30.1?
Oh, hang on. I got 30.1, and that's grams. Now, careful how you type it in. Okay, order of operation calculators are very, very specific. So if you do 744 divided by 0.622, thank you. Okay, because again, once you hit that times 397, the calculator does this divided by this, and it gets a number, and then it multiplies it by 397. So make sure that you do what Shane said, parenthesize that. Okay.
Parenthesize all of it, or?
Yeah, so whenever we hit the divided sign, remember back when we did factor labeling? Oh yeah, and we're going to see more of that when we do the final. So let me type it in again. Anybody else get that? 7.
I got your answer.
All right, practice problem number 2. Now this calculation which we're about to do is a type of calculation you'll do on the lab. Okay, so, and you'll have a chance, an opportunity to do that in your homework here. All right, so here's the question. It says a 147.3 gram sample of a metal at 103 degrees Celsius is placed in a calorimeter. Ooh, what's a calorimeter? It's actually, a calorimeter is something that we're going to use on Monday, styrofoam cup, that actually is an insulated system that absorbs energy. Okay, in other words, it's calorimeter, if you break it down, it's a calorie meter. So it absorbs energy, so we can, I know, right? So it's a thing that we can use to help measure how much energy is either lost or gained. So the sample is placed in a calorimeter containing 156 grams of water at 19 degrees Celsius. The temperature stopped changing at 24.4. And then it wants to know what is the specific heat of the metal. So let me actually draw what this is going to look like. So on Tuesday for you guys, I think it is.
Yeah.
Okay.
What's that? Is that a nice cube?
I'm an artiste, let me tell you.
That
Yeah, that's water. No, that's our solid that's in the water. For whatever reason, it seems to be levitating. All right, so let me actually write down what we know about this. So we'll have a beaker that's suspended above a Bunsen burner. It'll be levitating quite mysteriously. So we'll have our Bunsen burner with water. I'm sorry, we'll have our beaker with water that's boiling. And with using not distilled water, it'll actually boil at a higher temperature. And based on some of these thermometers, it might not boil at above 100. But we're going to place this metal, which is not capable of generating its own heat, into boiling water so we can get it to 103 degrees or whatever temperature we can get it to. So what we've got is a mass of a sample that is 147.3 grams. The temperature of the water, or the initial temperature of the metal and the water, because again, since metal can't create its own heat, it only absorbs the energy in its surroundings. So it's at 103 degrees Celsius. We don't care how hot the flame is. We will never take the temperature of a flame in here. We have a calorimeter over here that has 156 grams of water in it, and that's water. And it's at a temperature, an initial temperature for it at 19 degrees Celsius. And I think that's... And then what we're going to do in the lab is we're going to carefully and quickly transfer that metal from the beaker that has boiling water in it into calorimeter. We don't care if we get water out of this, but we don't want to splash water out of this. Okay. So once we place the solid in here, okay, the temperature of, not the metal, but of the water, temperature of the water changes to what? 24.4 degrees? Okay? And that's what all the data is saying, okay? So again, we start off with a metal, we place it in this quote-unquote room temperature water. When we place a warm object in there, does that make sense that the water temperature would go up? Yeah, because again, if it's not capable of generating its own energy, whatever's around it or in it will absorb that energy if it's at a warmer temperature. So probably the best thing to do now is to create, actually, can I erase that?
No.
Knock yourself out.
Thank you. Now I'll do it over here. Let's make a table. Okay, make sure it's in the picture here. So we're going to have water and our metal. Okay? And I'm going to go with mass, initial temperature, final temperature, and then the specific heat value. Okay? And we're going to organize and put values into all
That's what
these.
we should do in our paper.
Yeah, but do it kind of, don't take up the whole space. Take up like maybe a small section. So the mass of the water, and again, this is the calorimeter water. Okay, we don't care about the water in the beaker because it's going to be boiling and changing. So the mass of the water in the calorimeter, we said was 156 grams. What was the mass of the metal? 147.3. The initial temperature of the water in the calorimeter was 19 degrees. And the initial temperature of the metal was what? 103. So whatever its surroundings was. So 103 degrees Celsius. What was the final temperature of the water in the calorimeter? 24.4. What was the final temperature of the metal? Exactly, the same. In other words, what's going to happen is it'll lose energy until it's the same temperature as its surroundings, unless it has the capacity to generate its own heat. Now, I don't think I gave this to you, but the specific heat value for water is 4.18, actually it's 4.184, and that's joule, gram, degrees Celsius. Okay, so that will always be provided for you. That's a standard, 4.184. And we're actually looking for the one for the metal. Okay, so we have our table there, and yeah, we'll do it from here. So what's the question asking? It's asking for the specific heat value. So the first thing I need to do is I need to first of all find out what? Well, in the equation that we're going to be using is this. And I said that you'll always have 3 of the 4 variables. So which of these columns has at least 3 of the 4 variables? Now, don't forget that this is one variable. That's delta T, right? So which of these columns has 3 to the 4?
H2.
Yeah, this one. It actually has the mass, it has the specific heat, and the change in temperature. What we don't know is the amount of heat. Okay. So let's use the information from the water here. So Q equals MC delta T. And what this is it's the Q for the calorimeter. I put cal on there. So we don't have to rearrange these variables, do we? No, because we're looking for Q and we have these three. So the mass, 156. The specific heat, 4.184 joules per gram degree Celsius. And the change in temperature goes from 19 to 24.4, so what is that, 5.4 degrees Celsius. So what will my unit be once I calculate that? What's my unit going to be? Joule. Grams will cancel, degrees Celsius will cancel, so we're left with joules. So the Q for my calorimeter will be some value. So 156, 4.184. So around 3,000, and we don't want to round this number yet. If we can keep this in our calculator. So 3524.6016, and that's joules. Since it's not our final answer, we don't want to round it yet. Okay. So now we know the Q of the calorimeter. And this is a really important concept. How much energy, and I erased the drawing, how much energy did the calorimeter absorb? That's what this is saying. This much energy, right? How much energy did the metal lose? That much energy, very good. So what this is saying is, the energy that the calorimeter absorbed is equal to the amount of energy the metal lost. Okay? So now we have our Q value for our metal. So now we have Q, we have our mass, we have our delta T, now we can look for our C for our metal. Okay? And I think we need to erase that. Does everybody have that?
Hold on.
Okay. All right, everybody have that? So now, when we get ready to do our calculation for our C, so again, we have our equation that looks like this. How would I rearrange that so I just have C by itself? Divide the mass and the delta T. And notice that Q is always on top. Q is always on top. Q is always on top. So if you're wondering, I had that inverted, Q is always on top. So that's equal to our C. So we're going to use the same Q value, so our 3524, whatever's in your calculator, joules. The mass of the metal is 147.3, and that's grams. And the delta T, what is that, 24.4 to 103? Is that 70? Is that 78? What is that? Can make me do it?
78.6.
Thank you. So 78.6 degrees Celsius. And what will my unit be for this?
Joules per gram degree Celsius.
Nothing cancels. Very good. So our C will be in joule gram degree Celsius, which is an odd unit. Trust me, it is odd.
Make me run out of room.
I don't know if I can trust you.
So point.
Where's your 1736?
I'll say 304.
103.
Okay. So 0.304, and that's joule per gram degree Celsius. The reality is metals rarely get above 1 for specific heat. Metals are a terrible holder of heat, so to speak. Okay. Water's awesome. That's why it has such a high value. Because it takes a long time for it to heat up, but it also takes a long time for it to cool down. Okay? So now you have two different types of problems there. And let me give you a heads up here. Question number 4 is like this one. So if you want to circle number 4, 4 is like this. And number 7 is like this. Do you have to do a chart? I would. I always do a chart whenever I work a calendar or opera map. Circle number 6. Don't cross it off. We will work number 6 out together as a class. Okay. So put like a star next to that. We'll work number 6 together. But everything else should be okay. Oh, one other thing. The units must be in joules. They must be in grams. Okay. So if you're given something in kilojoules, convert it to joules. If you're given something in kilograms, convert it to grams. If you're given something in milligrams, convert it to grams. So we always want to go to these units. And it's a good refresher for the final that's coming up. Okay?
The Great Mega King.
Yeah, the Great Mega King one day caught me microwaving nasty pizza.
The Great Mega King.